Dirk Morr is a professor of physics at the University of Illinois at Chicago. His research in the area of theoretical condensed matter physics focuses on the evolution of complexity from the nano to the macro scale. Dr. Morr is a fellow of the American Physical Society, the German Alexander von Humboldt Foundation, the German Academic Exchange Service, and held the Leibniz Chair at the University of Leipzig, Germany in 2011-2012. From 2003 to 2010, Dr. Morr was a member of the task force that developed the new Science Storms exhibit at the Museum of Science and Industry in Chicago. His public engagements include popular science talks in which he does not only discuss the mysteries of the quantum world, but also examines the relationship between art and physics. Please now join me in welcoming Dr. Dirk Morr to the stage.
Thank you. Good evening. I'm glad you're here tonight and will share with me some of the exciting science behind Star Wars. Now, Star Wars is a story that has excited us and engaged us for more than 40 years. And it's actually a story that is as old as the Bible, since it's the fight of good versus evil. But it's a fight of good versus evil that is fought with a mystical force, with lightsabers, with starships, and with robots, and with weapons of unimaginable power of destruction. What I want to tell you tonight is a little bit the science that underlies all of these things, the force, the computers, the robots, the lightsabers, and see how realistic they actually are from our perspective, from the perspective of what we know about science, and in particular physics. Before I tell you more about this, let me just introduce the main protagonists. I'm sure that most of you are familiar with them, but there are two sides, the good and the bad, and the good is the light side of the Force. The light side of the Force is represented by the Jedi, a noble order of knights that preserves the order and law in the galaxy. And here we have Yoda, a master Jedi, and Obi-Wan Kenobi. And the Jedi are helped by the rebellion. There's Rey and Luke Skywalker, Princess Leia, Han Solo, and Jyn Erso. The counterparts, the bad people in the story, are the Sith, Darth Vader, the Emperor, Darth Sidious, Kylo Ren, and Snoke, and they're helped by the Galactic Empire and their stormtroopers. So these are the two sides that fight in this internal fight of good versus evil. And let me immediately jump into one of the central themes of Star Wars, which is the good and the light and the dark side of the Force. Now, who could tell us better what the Force actually is but Yoda, who is one of the master Jedi?
For my ally is the Force, and a powerful ally it is. Life creates it, makes it grow. Its energy surrounds us and binds us. Luminous beings are we, not this crude matter. You must feel the Force around you. Here, between you, me, the tree, the rock, everywhere. Yes, even between the land and the ship.
You want the impossible.
So Yoda tells us that the force is actually a life force that surrounds us and obviously allows us to move objects. So let me ask as a physicist, what is actually a force? And this question was more than 330 years ago answered by Sir Isaac Newton, who wrote about this in his famous oeuvre, which is called Philosophiae Naturalis Principia Mathematica. And he discovered that a force is always present when objects are accelerated. So whenever you apply a force to an object, you accelerate it. And if you want, that is a signature of when a force is actually present. And he formulated a very important law, which is called Newton's second law, that says that the force applied to an object is equal to its mass times its acceleration. Now, we're all familiar with that, right? Because if you take a baseball and you want to throw it, and it shouldn't really fly very fast, right? You give it a little push. You don't really exert a lot of force. But if you really want to fly it very fast, you have to really go into it, and you have to really use a lot of force to accelerate it, right? So this law is actually something that is very familiar to us. But we can think about it, how does it actually work? So I exert a force on this remote here. I'm holding it up, and if I had a ball and I want to throw it, then my finger basically makes contact with the ball, and I transfer force onto the ball to accelerate it. Right, so we use force every day, but we have to make contact with the object that we actually want to accelerate. But there are other cases where there is no contact, and one of those cases you are very familiar with, of course, namely when we look at the moon that circles around the Earth, there's obviously no string attached. There is no line that connects the moon, that keeps the moon on the circular orbit around the Earth. So how does it actually work? Because the Earth actually exerts a force. Without the gravity of Earth, the moon would not circle around the Earth. Now, this is a very interesting question, and we have some ideas about this. One idea is that the force is actually transferred by the exchange, or mediated by the exchange of particles, which we call gravitons. So there's a constant stream of these particles, which are subatomic, that is exchanged between the Earth and the moon. And this exchange of particles leads to gravity. It makes sure that the moon will remain in its orbit around Earth. So the forces are mediated by this exchange of particles. Now it turns out that gravity is not the only force which is mediated by particles. Actually, there are 4 fundamental forces in nature that we know of today, which are mediated by particles. So I talked about gravity or gravitation. Then there's the electromagnetic force that you're familiar with. You charge particles. If they have the same charge, they repel each other. Then there is the strong and the weak force. The strong force is responsible for nuclei, the nuclei of atoms actually staying together. And the weak force is responsible for radioactive decay. And these forces are mediated by gravitons, which I already mentioned, by photons for the electromagnetic force, by gluons for the strong force. Glue, not very inventive, but it conveys the point. And by the so-called W and Z bosons for the weak force. Now, all of this is put together in what we call the Standard Model. Now, the Standard Model has quarks that you might have heard about. They basically make up the neutrons and the protons, which by themselves make up the nuclei of atoms. Then there are the leptons, the electrons, which is also part of an atom. And then there are these, what I call gauge bosons, but there's this gluon, which is here. There's the photon here, and the Z and the W boson. And it is this Standard Model that actually describes a lot of our understanding, or encompasses a lot of our understanding of how atoms are built and how matter is actually built and what it is made up of. So the question is, does this actually explain all? And we don't really have to go very far. We just have to look at the list that I gave you, and you immediately notice that the graviton is actually not part of the Standard Model. right? So gravity is actually not part of the standard model, and one thing that we are pursuing as physicists is to find another model that actually would allow us to put gravity and the standard model into a single framework. Right? So at least there's one particle that actually is not part of the standard model. So the answer is, does this explain all? The answer is no, but it is even worse, or as we physicists say, it's even more exciting. Because it actually turns out that we only understand a small part of the universe. And honestly, if we understood all of the universe, we would be out of a job. So it actually turns out that we only understand about 4.9% of the universe. This is actually the conventional matter, right? The stage, the air around us, this remote, this is conventional matter. And only 4.9% of all the matter, of all the energy in the universe is actually made of this conventional matter. There is other matter, which we call dark matter, which makes up 26.8% of the universe, that we have honestly no clue what it actually is, hence the word dark matter. If you want, it's a physicist's fudge factor. Now, we stipulate that this dark matter has to exist because galaxies actually are rotating much faster than they should if we just used the gravitational forces that are present due to the matter that we can observe. So something actually allows galaxies to rotate so fast as they do, which is not visible, and this is called the dark matter. But there's another problem, namely that for a long time we thought that the universe is actually slowing down in its expansion, but it actually turns out it's accelerating. And to explain that, we need something else, namely dark energy, which actually makes up the bulk of the universe. So they're 68.3%. Of course, these are estimates. But it actually turns out that we only understand about 1/20 of the universe in terms of the standard model. So this means that there's definitely still so much to discover, so much that we don't understand, so much that does not fit into the standard model, and maybe even one day we will discover a mystical force, something along the lines of what Yoda described. Now, another very exciting aspect of Star Wars are the lightsabers.
If you will not turn to the dark side, then perhaps she will.
So this was the final fight of Luke Skywalker, who represents the light side of the Force, against Darth Vader, who represents the dark side of the Force. So can we actually create these lightsabers? Again, before we even start thinking about this, we have to ask the question, what is actually light? And this question was answered about 150 years ago by James Clerk Maxwell, who showed that light is actually nothing else but an electromagnetic wave. So it's actually very similar to a wave that we see every day in Lake Michigan, or if you throw a stone in a pond. But it is on a much, much smaller scale. So here, a wavelength, the distance between the crests of a wave might be, a foot or 2 feet or a yard. But the length scale of the wavelength for electromagnetic waves for light is actually much smaller. So if we just look at this little representation of a wave, and if we say, so the wavelength is basically the length between one crest of this wave and another one, we call this lambda. It's a Greek letter by which we denote this wavelength. then the first thing that we realize is that there is a difference between the light that represents red and the light that represents blue. Namely, when you have different wavelengths, you have different colors. So for example, if you have blue light, you have a wavelength about 500 nanometers. So a meter is about a yard. It's a little bit more than a yard. And a nano, as a prefactor, is a 1/billionth. Right? So we are basically talking about 500 1/billionth of a yard. So that's a very, very small length scale. Now, if you look at red light, it actually has a larger wavelength, about 700 nanometers. But it's clearly nothing that you can see this wave with your naked eye. But how do we know that light actually has the same properties as waves? Because we can do experiments and essentially the same experiments that we do with waves that we can also do with light, and both waves, water waves and light waves, behave very similarly. And this is how we know that indeed what Maxwell showed 150 years ago is correct, namely that light behaves like a wave or is an electromagnetic wave. Okay, so we now understand what light actually is. What type of light do we actually need to build a lightsaber? So let's look at the sun, and let's look at sunlight. Now, it turns out that the sun is constantly emitting light, and at all points in time, and this light is actually not ordered. So what I mean by this is that, for example, the crests of these waves do not really align. Right? So we have crest here, which actually coincides almost with the minimum here. And then, because they don't align, we say that the sunlight, is actually disordered, or we also say incoherent. Okay? So this is the light that comes from the sun. Now let's look at something else. Let's look at a laser. Should look at a laser. You all know that physics is when it doesn't work. Okay, why doesn't it work? Okay, I think this means that the batteries are empty. So let me then just tell you that if we now take oops, maybe it's not the battery. Okay. Let's try this again. Let me just see what it is. Thanks. Here we go. Problem solved. Okay, so now let's take a laser, and let's compare the laser light actually with the sunlight. It turns out that the laser light is actually ordered, which means that all of the maxima or the crests of these waves actually align. And because laser light is ordered, or we call this coherent, it actually turns out that it is much more powerful than sunlight. Okay. So this basically means, okay, obviously in Star Wars, lightsabers are very powerful, right? So why don't we actually use a laser to build a lightsaber? Well, the problem is, as you have also seen from these little animations, that light actually does not stand still, right? It just travels, whereas these lightsabers seem to be just stationary, right? Almost like swords, but made out of light. Okay, so obviously we have a problem, namely that even if we took a laser and we were emitting light, it wouldn't stand still. It would just travel forever. Okay, so how do we solve this problem? Well, everybody of you who plays a string instrument, of course, knows the answer to this. We are just creating what is called a standing wave. And with the laser, we do this basically by taking the laser, and now we take two mirrors. So what happens is that the laser will actually now let the light go through the first mirror, and then the light actually bounces back and forth between these two mirrors, and we call that a standing wave. Right? So we basically prevent the light from escaping. And because we trap now the light between the two mirrors, we can actually create large energy densities. We can trap a lot of energy between these two mirrors. Okay? And then maybe we can create something like a lightsaber. The only problem is that it seems that we need mirrors to actually trap the light in between. Okay. So do lightsabers actually use mirrors? Let's check. Definitely no mirrors. So I'd say that's probably a technology that we don't really know how to create. Good. Let's come to one of my favorites, traveling with the speed of light.
Stop that ship! Blast them! Chewie, get us out of here!
Oh my, I'd forgotten how much I hate space travel. How long before you can make the jump to light speed?
Take a few moments to get the coordinates from the navicomputer.
Are you kidding? The rate they're gaining?
Traveling through hyperspace ain't like dust and crops, boy. Without precise calculations, we'd fly right through a star or bounce too close to a supernova and then it injured trip real quick, wouldn't it?
What's that flashing?
We're losing their deflector shield.
Both strap yourselves in. I'm going to make the jump to light speed.
And off they go to save the galaxy. So why don't we have that, right? Wouldn't it be nice if we had these starships with light speed? We could just go to the next star and investigate a little bit. So why don't we have this? Well, if you want to blame somebody, you have to blame this gentleman, Albert Einstein, because he formulated something more than 100 years ago, which at first sight looks pretty innocent. He said, no matter how fast you travel, the speed of light is always the same. And he formulated this in 1905, and this then led to the special theory of relativity. Now, there's always this problem in physics that these innocent-looking little sentences, like this one here, actually have pretty big ramifications. And to tell you what the ramification is, let's actually first stop here for a second and think about whether this is not a little bit strange, that the light speed is always the same. It definitely is counterintuitive to our experience, to our daily experiences. And to show you why it's counterintuitive, we asked this lady, Marie Curie, who is a French physicist, to help us out. And Marie really likes to play ball, in particular baseball. In particular, she likes to really throw these baseballs very, very fast. But she also likes to challenge her friends. And so she first challenges Albert, who likes, by the way, to drive in a VW Beetle. And she says, OK, let's see whether you can drive faster than I can actually throw this ball. And Albert says, why not? Let's do this. But this is not quite fair because the VW Beetle is not the fastest car. So why don't we ask another one of our colleagues, namely Lisa Meitner, to join us. And Lisa really likes to be on these fast German trains, these ICE trains. OK, so Lisa likes to ride these trains. And now Marie says, OK, I'm going to throw the ball. And you drive on your VW Beetle or in your ICE train. And let's see who is faster. OK, let's see what happens. So Marie throws the ball, Albert and Lisa are riding the car and the train, and then they all come back and Marie asks, how fast did the ball actually fly? And Marie has a pretty strong arm, so she said, well, I stood still, but I counted 100 miles per hour, which was bad. Albert drove 50 miles per hour and said, well, from my perspective, the ball actually flew with 50 miles per hour speed. right? So you see, he drove with 50 miles per hour, and he said the ball flew 50 miles from my perspective. And if you add these two things up, you get 100 miles that Marie actually threw the ball with. And now we asked Lisa Meitner, and she said, well, I was on the train, and the train was going 100 miles per hour, and from my point of view, the ball was completely stationary, so it didn't move at all, right? And again, if you basically add up Lisa's speed, 100 miles, plus what she thinks, how fast the ball actually flew, which is 0, you again get the 100 that we had up here. Okay, so then Marie said, let's try something else. Let me take a flashlight, and now I will send out a light wave, a flash of light, and let's see who is faster. So obviously, the flash of light was faster. And now Marie says, okay, so how fast did the light actually travel, right? Keep in mind that 2 minutes ago, I told you with the ball that Albert and Lisa actually measured different velocities or different speeds for the ball. And so Marie said, okay, I stood still, and the speed of this light ray was 186,282 miles per second, so pretty fast. Then we asked Albert, who was again driving 50 miles per hour, and he comes up with exactly the same number. So he actually measured the speed of light while he was moving, and he finds the same result as Marie. And then we asked Lisa, and Lisa drove with 100 miles per hour, and again, she finds exactly the same value for the speed of light. So independently of how fast Albert and Lisa actually drove, they measured always the same speed of light. So that is very different from the example that I just gave you with the ball. So how is this actually possible? Right? How is this possible that you actually always measure the same speed of light? Now, it turns out that as you actually start moving, time actually slows down for you. Right? Time passes more slowly, and this means that because time passes more slowly, you can always measure the same speed of light, because the speed is distance traveled divided by the time, and if the time changes, then also the speed changes. Now, how do we actually know that this is true? Well, we know that it's true because we can take two completely synchronized clocks, and then we put one on a plane, and we send it a couple of times around the Earth. And then when the plane stops, comes back to the initial position, we can now actually compare the two clocks, and we actually find that the one that was on the plane that was actually moving is now a couple of nanoseconds slower than the clock that actually remained on the Earth. Right? So time actually changes depending on how fast you actually travel, and this ensures, if you want, that the speed of light that you measure is always the same. Now, the other problem is, and this is actually what prevents us from going as fast as the speed of light, is that as we go faster and faster, our mass, our weight, if you want, actually increases. Right? So let's assume something is 1 pound and it's stationary. And here, this is on the horizontal, we basically have your velocity divided by the speed of light. Right? So here, you're as fast as the speed of light. And so you see that as you accelerate, you get faster and faster and faster, your mass, which had 1 pound before, it actually becomes larger and larger and larger and larger, and eventually just diverges. Which means that as you approach the speed of light, you need more energy to become faster, which means you increase your weight, your mass, which means that you need more energy, and so on and so forth. And so you actually never reach the speed of light because you simply get heavier. Right? So this is actually the problem with not reaching the speed of light that prevents us now to do what Han Solo and Luke Skywalker did in this clip that I just showed you a couple of minutes ago. So the question is, can we ever overcome this barrier? I don't know. But let's look at history for a moment. I like history. So what has history actually shown us? History has shown us that scientific progress is completely unpredictable. And let me give you one of the really great examples of this. This was published by the New York Times. And it says, it might be assumed that the flying machine, which will really fly, might be evolved by the combined and continuous efforts of mathematicians and mechanicians in from 1 million to 10 million years. Right? Reputable newspaper. And this was published on the 9th of October, 1903. The problem with this prediction was that barely 3 months later, the brothers Wright, of course, flew for the very first time. Right? So this is a very nice example of how scientific progress is actually unpredictable. And it's also a beautiful example of the lack of imagination. Right? The only thing that separates us from finding a way to reach the speed of light, or even exceed it, is one brilliant idea. And whether somebody will formulate this idea tomorrow, in a year, or in 100 years, we don't know. That's the unpredictable part. So coming back to the question, will we ever be able to travel faster than the light? We don't know yet. But I would say history is definitely on our side, because there have been many barriers of which we thought we would never be able to break, and we eventually did. Good. Let's come to one of the weapons of mass destruction in Star Wars, the Death Star.
Governor Tarkin, I should have expected to find you holding Vader's leash. I recognized your foul stench when I was brought on board.
Princess Leia, before your execution, I would like you to be my guest at a ceremony that will make this battle station operational. No star system will dare oppose the Emperor now. Since you are reluctant to provide us with the location of the rebel base, I have chosen to test this station's destructive power on your home planet of Alderaan.
No, Alderaan is peaceful. We have no weapons. You can't
You will
possibly...
prefer another target, a military target? Then name the system. I grow tired of asking this, so it'll be the last time. Where is the rebel base?
Dantooine. They're on Dantooine.
There, you see, Lord Vader, she can be reasonable. Continue with the operation. You may fire when ready.
Commence primary ignition.
So the question that immediately arises from this, can we actually destroy a planet? Right? Can we actually destroy it and scatter the stones, the lava, whatever makes up a planet across the galaxy? Now, as a physicist, the question is, how much energy do I actually need to do this? Right? Because I take all the stones, but essentially what this Death Star does is it sends so much energy that all the stones, the lava, whatever makes up a planet just fly in all directions. Right? And to do this, you have to count what we call the gravitational energy, because if I want to, again, use this remote here as an example, if I want to remove it from the Earth, I have to accelerate it, I have to exert a force, I have to give it kinetic energy, I have to give it speed energy. So how much energy do we actually need to destroy a planet? Now, as a warm-up, let's first ask a different question. How much energy does it actually take if I wanted to remove the moon from its orbit around the Earth? Right? So I just want to push the moon infinitely far away from the Earth, and I ask how much energy does that actually require? And you can actually calculate this, and it turns out that the energy that you need is 8 times 10 to the 28th joule. That number doesn't really say much, right? Joule is the unit of energy, and 10 to the 28th means you have a 1 with 28 zeros behind it. But it doesn't really mean much. But we can actually put this in terms that we can understand. Namely, this is the world's energy consumption for about 100 million years. Right? So that's quite a bit of energy that we actually need if we wanted to move the moon away from its orbit around Earth. So, but in the Death Star, we do something else, right? We basically just tear the Earth or planet apart and and scatter it across the galaxies. And it turns out that if you want to do this, you need more energy. You need 3 times 10 to the 32 joule. Right? So that's a 1 with 32 zeros. It's a lot of energy. And again, we can ask, can we actually put this in terms that we might understand? It turns out that this is the total energy that is created by the sun in 8.5 days. So not only the energy that actually arrives from the sun on our planet in 8.5 days. No, it's the total energy created by the sun in 8.5 days. Right? So it's an unbelievable amount of energy. And I don't know of a battery, such as the Death Star, that could actually hold that much energy. But somebody must have actually told the creators of Star Wars, at least in The Force Awakens, that there might be a problem with this energy scale, because they were smart enough to use this to actually show that their Death Star has to be charged by a star.
Begin charging the weapon.
Yes, sir. I've been charging.
Okay, so again, we need so much energy, there's no battery that exists that could actually hold this amount of energy. So in other words, old technology that is pretty impossible to generate. Good. Now, another of my favorite is actually the artificial intelligence that is described in Star Wars.
Did you know that wasn't me?
Of course.
I thought I told you to stay on the ship. You did, but I thought it was boring and you were in trouble. There are a lot of explosions for 2 people blending in. Freeze, right there. You're right. I should just wait on the ship.
Yeah. So the funny thing is that these robots, the artificial intelligence, actually has a good sense of humor. So how would we actually do this? How would we actually build artificial intelligence? We think that we as humanity are intelligent, and this all takes part in our brains. So if we want to create artificial intelligence, we first need to understand understand how our brain works. And so what we do is we actually take our brain, and our brain is made up of neurons, and the neurons basically transfer information around in our brain. And so we describe our brain as what is called a neural network. Basically, this just means that we have these dots, these points, and we create a network, we connect them, and each connection basically allows the flow of energy and information. So information can flow from here to here or from here to here, but only between the dots that are actually connected. So by mapping our brain onto these models, we are trying to understand what kind of connections need to be made in order to process information. And the question then that we want to understand is, how does information actually flow in these networks? And it turns out that that question is connected to the degree of connectivity. How do you actually connect these blue dots? Do I connect this with this one, but why don't I connect this with this one? And how you connect determines how information actually flows through this network, which is a model for our brain. To give you an example, I will actually use an example of what we did in my group. I don't work on brains, but we have actually done work on networks. And I want to give you an example that I worked on with one of my graduate students, Tankut Khan. So this is a small network. These are, if you want, are the neurons. Each blue dot is a neuron. And I want to send information into this network here on the left, and it should come out on the right. And the first thing that I do is that each blue dot I only connect to its new nearest neighbors, one left, one right. And when I do this, then the information goes in here, and either the information flows down here, or the information flows up here, but there is no other way. There are only two ways in which information that enters can actually go through this network. Okay? Very simple. So now let's see what actually happens if I connect more dots. Let's assume I connect every dot in this network now to 16 other dots. There are a total of 20 dots in this network. And now I calculated how information will actually flow, and I see something which you could call higher complexity, or you could call disordered. Right? This is not as nicely ordered as this picture here. And now every dot is basically connected to other dots, and so you can have information that flows from here to this dot, from this dot to this dot. And there's not much of a pattern that you can actually see. But now I do one thing. I allow each of the dots here to be connected to one more pair of other dots. So rather than being connected to 16 nearest neighbor dots, I now allow them to be connected to 18 nearest neighbor dots. And I again calculate the flow of information, and I find this. So this now looks very different, right? I mean, at least for my sense of aesthetics, this looks ordered, similar to this one, whereas this one here looks really disordered. But this is a very nice example of where you just do a small change, right? We go from 16 to 18 neighbors. You actually see that the pattern completely changes. It becomes much more symmetric. And we say that this increased connectivity actually creates emerging novel properties that we could not have predicted. Now, many of you are probably familiar with this, right? Particularly those of you who have kids. Because when we see our kids grow up, every day there are no more connections made in our kids' brains. One day they cannot ride a bike. The next day, when more connections are made, they ride the bike as if they've ridden it for the last 10 years. One day they cannot read, and the next day they read Shakespeare. And the transition between these steps is actually very abrupt, but it is made actually by small changes here between 16 and 18 nearest neighbors that I connect my network in. Right? And the question is now, of course, which networks do we need to really create artificial intelligence, and how do we actually connect the points in this network? And that is a question for which we really don't have an answer yet. That is a question of ongoing research. Now, another interesting part of Star Wars, all the foreign planets that are described in the Star Wars universe.
Coruscant. The entire planet is one big city. There's Chancellor Valorum's shuttle.
I didn't know there was this much green in the whole galaxy.
How did we get into this mess?
Good question. So you've seen in the Star Wars universe, there are planets which are completely made up of deserts, or of water, or of woods, or of cities. Right? And of course, the question that underlies all of these planets is, are we actually alone in the universe? Right? Before we can actually answer that question, we first have to discover planets. Before we can discover life on them, we have to discover whether there are actually other planets. And these planets are called exoplanets. And over the last decade, we actually have discovered a lot of these planets in faraway stars, or around faraway stars. So how do I actually do this? A famous principle is called the light-on, light-off principle, or also called transit photometry. It's actually very simple. Namely, let's assume I want to figure out whether there is a planet circling a star far away, a couple of hundred light years away. So there might be a planet, and I'm on our planet Earth here. So how do I actually detect whether there is a planet around the far distant star? Well, every time a planet actually circles the star and blacks out a part of the star, I perceive the star to become dimmer. Right? It decreases its what we call the luminosity, and you can actually measure this. What you see here is for a star. It's called Kepler 444. It's about 160 light years away. So that's the distance that light travels in 160 years. And it has 5 planets. And what is plotted here is what we call the luminosity, how light is actually the star. And you see that the star has some luminosity, and then it decreases, and it decreases. And every of these 5 instances represents an event where one of these 5 planets actually is in front of the star and makes it a little dimmer for us. Right? So this is one of the many ways now we can actually use to discover new planets, exoplanets. And as I said, we have actually discovered a lot of them. And of course, the question is not only do stars have planets, but which of them are actually habitable, right? Which can actually sustain life. And in order to kind of at least estimate or approach this question, we use a very famous principle that most of you are probably familiar with. It's called the Goldilocks principle. Right? Because the first thing, if we want to look at habitable planets, or can planets actually sustain life, we start with our life. Our life on Earth is based essentially on water. Right? So this means that if it's too cold, water freezes below 0 degrees Celsius, 32 degrees Fahrenheit, right? Or it becomes a vapor at 100 degrees Celsius. So we basically have about 100 degrees to play with. And so if a planet is in a range from a sun that would allow a temperature at its surface somewhere between 0 degrees Celsius and 100 degrees Celsius, then there's a chance for life, at least water-based life, to exist. And this is called the Goldilocks principle because it can't be too hot and it can't be too cold. It has to be just right. And what you see here is actually from the Kepler telescope, a number of planets that were discovered in this green area. So this is on the vertical here is the temperature of these various suns. And on the horizontal is how far these planets are actually away from the sun. And each dot here represents a planet. And this green area is the area where the temperature on the surface of these planets is just right, which means that water, liquid water, could actually exist. And there are now a number of exoplanets which fall into these green areas. And this is kind of a cartoonish rendering of all of these planets. We, of course, don't know what they actually look like. But there are a number of habitable planets, or at least potentially habitable planets, which have been discovered over the last decade. Now, the question, of course, is now we know that there are habitable planets. Is there intelligent life out there? So this is a question that we want to answer. And whenever physicists encounter a question to which they honestly don't have an answer, what do? We write down an equation, right? And this is called the Drake equation. And the Drake equation says, well, the number of intelligent, or the number of planets in which intelligent life can exist is equal to the number of stars times the probability that a star has a planet times the number of planets that are habitable times the number of those planets which can actually sustain life times the number of those planets that can sustain life on which intelligent life can actually develop times the number of those planets in which life evolved and actually can communicate times the time, the lifespan of these populations of these planets, right? So definitely, if you knew all these numbers, you could definitely come up with a number of intelligent civilizations in the universe. And so we can estimate all of these different ingredients to this equation here. And so we can get an estimate. And an estimate always has an upper boundary and a lower boundary. So the upper boundary for this estimate is about 15,600,000. That's a good number, right? So we basically say, well, there might be 15 million planets out there that actually have intelligent life that we can make contact with. Well, that's the upper boundary. The problem is the lower boundary. If we look at the lower boundary, then that is 0.000 and so forth, 1. So it's essentially 0, right? So this equation is great. The only problem is that there is so much uncertainty in all of these products, in all of these numbers, that we can really not get a good estimate. This looks good. This means there's none. So again, the question is open whether there is intelligent life besides ours in the universe. So with this, we have to come to the question, what is next for us? I gave you a little bit of a review of the science that is described in Star Wars that might be possible or might not be possible, standing where we are with our knowledge nowadays. So what is next for us? Will we discover new particles, new subatomic particles that will allow us to develop a new framework in which the standard model can actually coexist with gravity? Will we find new materials that allow us to send energy without any losses over thousands of miles? Will we understand how nature actually works, how our ecosystems actually work? Will we discover new exoplanets or discover new sources or better sources of sustainable energy? We don't know. Progress, scientific progress, is unpredictable. But what is clear is that scientific discovery is and will remain a very exciting human endeavor. And with this, I'd like to thank you for your attention.